Welcome to Mathematics with Tom. This is Tom, and in today's video we are going to talk about vector spaces. Vector spaces. Okay, we've been working with some vector spaces, but I want to give you some examples. So examples of vector spaces. Examples of vector spaces. And we often use a capital V to denote a vector space. Okay. Examples include the real R2. We've been working with R2. They include R3, and we've been working with that. They include all the way up to even Rn. And now remember, for all of these, if we say that x, the vector, is an element of Rn, then what that means is it means that x is the vector with n components. So x1, x2, it could have x3. It could have as many as you need, down to all the way down to xn. xn. Okay? And so that's what it means to be a vector in one of those spaces. Now, what other examples include, we're going to use same notation that our author is using, and that is M, where M is the set, or I should say not set, but let's call it the vector space, is the vector space of all 2 by 2 matrices. All 2 by 2 matrices. Okay. Another one is F. F is, and I'm going to use the word set, or we'll use is the vector space F is the vector space of real valued functions. Real valued functions. And here, let's look at one more that might take you off by surprise, and that is Z. We're going to use capital Z, not like the Z used for integers, but just a capital Z. And Z is the vector space of the zero vector, Okay, now, vector spaces can contain vector spaces. And so we say this, a vector space in V is called a subspace. It's called a subspace S. Yes, so it's a vector space in a vector space. And then there can even be another one, but let's look at an example. So let's look at this. M is the vector space of all 2 by 2 matrices, A, B, C, D. Okay, that's what M is. And we're going to say this is the vector space V, and provided that, so that's what this vertical bar means, provided that it's that matrix given that A, B, C, D are any real numbers. Okay, so that's what the set of all 2 by 2 matrices are. Now let's look at a subspace of that. So U is the subspace of M in that U is the upper triangular. So it's like A, B, D, and C now is permanently 0. Well, the set of upper triangular matrices is a subspace of V, where V is the set of all 2 by 2 matrices. It's a subspace of V. Call it S. But we can go even further. Define D, capital D, as the set of diagonal matrices. Well, that would be like A in the top left and a D in the bottom right, and then B and C now are 0. Is a subspace, is a subspace SS of, well, it's a subspace of a subspace, so it's a subspace of U, but it's a subspace of the subspace of V, which is the set of all 2 by 2 matrices. Okay, here we go. Let's take a look at an example and see how this works. Okay, so we're going to consider let's consider the vector R2. Now R2 is, we already said, is a vector space. So R2 is a vector space. Now, let's take a look at a space inside of that. Now here's what we're going to do. We're going to define our subspace S as the set of vectors x equal to let's do it like this. Let's do it like A and then 2A. So the first component of x is twice the second one, provided that A is any real number. Well, what is that? What is that? Another way of thinking of that is you could write this as x equals some scalar times the vector of 2, 1. Times the vector of 2, 1. Well, here's what we have to do, and that's our goal. Show S is a subspace. So here's what it means to be a subspace. There's a set of 10 definitions to show a vector space, and then to show it's a subspace, we have 3 that imply all those 10. So here's what they are. First off, number 1, we have to show that the 0 vector is in your subspace. Okay, that's the first thing. And we'll go through each one of these. 2. I have to show you that if I take a vector x and a vector y, where both of these vectors are in the subspace, then x plus y is x plus y. Who knows, maybe it's the vector w. Well, w is also in the subspace. Now we're going to put this idea together more closely here, because number 3 is very similar in that if I take any scalar, so c is any real number, and if I take c and I multiply it by x, then c times x has to also be in S. Okay, these are the 3 conditions we have to show. We're going to show you how they hold. And these last two are called the property of closure. The property of closure. And this is a subspace that we're going to look at, but then in our next example, we'll look at one that is not a subspace, and you'll see what closure really is. But closure means that we've had it so far, but closure means that the vector spaces behave as you would expect them. If I added 2 vectors, you're still in the same space. If I multiplied a vector by a scalar, you're still in the same space. And working in R2, since there's an infinite number of linear combinations and scalar multipliers, you can never, think of it as the idea of leave, but you cannot leave R2. So here we go. Let's show this. Now first, let's start with a picture. A picture, I think, is often a good way to visualize. So let's start with a picture with a, there we go, straight axis. And there's another straight axis. That first axis is kind of bent. So let's see if I can do a better one this time. That looks better. All right, and let's give it some tick marks. How about 1, 2, 3, 4, maybe 5. We'll go up the other way. 1, 2, 3, 4. Now if I've done this right, let's see. 1, 2, 3. We'll go down. 1, 2, 3. Okay, so let's graph this. I'm going to graph. We'll use yellow. Yellow shows up really nice. So let's just graph. Notice that really what we're looking at is we're looking at the set of vectors that are scalar multiples of the vector 2, 1. So let's put down that. So here is the vector x, and let's put an arrow on it. So x here is the vector 2, 1. Okay. But what we want to keep in mind is that, remember, if I took this vector x and I multiplied it by 2, 1, well, 2 times that, for example, would take me out to 4, 2. Well, 4, 2 is, everything is straight and lines up, 4, 2 would take me out to here. And I could go even further. I could go out to 6, 3 and all sorts of different values. I could get a half in there and maybe have a little vector down in here. But it also, I can multiply it by negative numbers, and so that vector is not restricted. The next one, easy one for me to graph on the way back down, is the vector -2, -1. And it continues. And so the set S, our subspace, is this line. This orange line is our subspace, again and it's really just all possible multipliers of the yellow vector 2, 1. Now let's put this together. Number one, and look at this. Let's look at our picture. Our picture says that the 0 vector is in the subspace. Is it? Right there. That is the vector 0, 0. Or if you think in general, you can also just write this. We'll just write it as the 0 vector. If you write it that way, you have to think contextually, meaning what space am I in is how many zeros are in the 0 vector. So you can see it's in there. How do we show? So how would we show that? Number one is we let A equal 0, then 0 times the vector x. Well, that's just going to be 0 times 2, 1. And that's just going to be the vector of 0, 0, which is the 0 vector. So we can say that the 0 vector is in S. Okay, that's how we satisfy the first condition. Number two says that if I take 2 vectors from the subspace, they're still in the subspace. Well, that subspace is a line. It's just that orange line. Is that really true? Let's try that. So let's think of this. Let's take an x and a y that are both in S. So for example, x, now usually you would use a general example, but I don't think we're quite ready for that yet. Let's use a specific example. So let's let the first one, let's use x as -2, 1. -2, 1. And how about y is the vector, we've already drawn it in there. How about 4, 2? 4, 2. So now if I add these, if I take x plus y, well, that's -2, 1 plus 4, 2. Well, if we add those together, I get the vector, -2, -1, sorry. That's the vector of 2, 1. Sure enough, that's the vector that this whole thing started with. That was too easy. Let's try the general approach now. The general approach would be that x is of the form 2 times a A. And y would be some other value, some other scalar. So y could be, we'll use c. How about c? So it'd be 2c and then 1c, or just a c. So let's see in the general case what this would look like. Well, if I take x and I add it to y, that's going to be 2a plus, that's my x, plus y, that's 2c c. Well, when I add those together, I can factor out a 2. Well, we'll write it. I'm going to write it this way. Let's write it as 2 times a plus c. And in the second one, I'm going to write it as a plus c. But wait a minute. Look at what the common factor is, especially if I put a 1 right down in the second component. This is the vector of, now I'm going to scroll up so I can get a little more space here. Leave it like that. So now I can say that, look at this, x plus y is equal to a plus c times the vector of 2, 1. Well, what is a plus c? A plus c is a real number plus a real number. Look at that, where a plus c is just another scalar, r. It's in R. And sure enough, then if you take any two vectors on that line and you add them, you're still on that line. And the final one, the final step is step 3. And step 3 says, if I take any scalar, c, and I multiply it by, and we should say, I should be more formal there. So if we take any scalar in the real numbers, then c times x is also in R. Well, let's check. So if I take c and I multiply it by x, that's c times, well, x is 2a, 1a. But that is the same as, oops, not plus, it's equal to, if I take the a, that's just a times c times 2 times 1. In other words, it's just a scalar multiple of x. And so you would say that, yeah, that's still in S. And that's how you show something as a subspace. So, and actually we're going to stop there and we'll do that in our next video. Thanks for watching.